Good afternoon, one and all. I, Lieutenant G. Somasundaravori, on behalf of Postgraduate and Research Department of Mathematics, Dwarakadas Govardhan Das Vaishnava College, welcome you one and all for the webinar series 3, so day 5. On the topic, A Journey on Entire and Meromorphic Function by Dr. Naveenkumar from Presidency University, Bengaluru. It is my great pleasure to invite for this webinar our Honorable Secretary Shri Ashok Kumar Mundraji and our beloved Principal Captain Dr. S. Santosh Babu and Convener and Head Department of Mathematics Professor R. Venkatramanan and all the participants and all staff members and all my colleagues. So now we start this program with a prayer.
சீராரும் வதனமென திகழ்வரத கண்டமிழே எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் கரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिः सतां दर्शनेस्तु भवत्तनूनाम् नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनामविभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
It's my great pleasure to introduce today's resource person, Dr. Naveenkumar S, Assistant Professor, Department of Mathematics, Presidency University, Bengaluru. He is having a research publication, totally 21, on the subject complex analysis, Corpus Index Journal 8, and Web of Science 2, then UGC Catalyst another 8. Added to this, he completed his doctorate in year 2019, he done his master's at Davangere University, bachelor's at Coimbatore University. He has also acquired so many computer skills and basically C, C++, Skylab, MATLAB and LaTeX and all. So he published in a different national and international reputed journals. The total number is 21 and he presented 6 papers in different workshops and symposium and attended 5 workshops and symposium. Is a vast work experience in University of Visvesvaraya College of Engineering, then Directorate of Correspondence Course of Distance Education, Bangalore University, and GATM University deemed Bangalore campus. And presently he is working at Presidency University, Bangalore. So now we have with us Dr. Naveenkumar. Sir, we are very happy, sir. So now
Thank you,
I
sir.
hand over the session.
Thank you, sir. Thank you very much. Good afternoon to all. A grand welcome to the session on a journey on entire and meromorphic functions. First, I want to start from the basic concept complex numbers. Complex numbers, the numbers which are explained in the form of x plus iy, where x and y are reals, and I is a complex number, imaginary number, square root of minus 1.
Sir, share your screen, sir.
Sir,
Your screen, sir.
is not visible, sir?
No, sir. Put a share screen, sir.
No, sir?
Yes, sir. Now you can put a full mode. Yes, sir. Thank you, sir.
Thank you, sir.
Thanks.
So first of all, I said complex number, the number which is expressed in the form of x plus iy, where x and y are real numbers and I is a imaginary number. I is equal to square root of minus 1. Then what is the history of this complex number? How it is introduced, implemented? What is the need? While finding the square root of a negative number, it gives the complex number. That meaning Cardan. It is the basic work from Cardan introduced this I value as square root of minus 1 while finding the square root of a negative number. Then after that, I said the number which is in the form of x plus iy, where x and y are real numbers and I is an imaginary number. In this way, from this definition, we can say real number is a subset of complex number. Suppose if I take a real number 2, we can write it in the form of 2 plus I into 0, complex number. If I take 3 plus I into 0, complex number. That's why a real number is a subset, set of a real number is a subset of complex number. What about a very complex number is real? May or may not be. That we can show by using the basic concepts. For that, I am going for another slide. Wait 1 second. Look onto this. See this one. Are complex numbers real? No, may or may not be. All complex numbers you cannot say real number, but all real numbers we can express in the form of complex number. That only is saying that whatever I said, that is you can see in the slide. I is equal to square root of minus 1. I square is equal to minus 1. And come to the next one. These are all how to locate the complex numbers. X plus z is equal to x plus iy. You can see x comma y. The point x comma y that represents the location of the or representation of the complex numbers. The real part we can say it as x, and the imaginary part we can say it as a y. And how to find the absolute value? That is square. These are basic things. Model of z is equal to square root of x square plus y square. And you can see the z is equal to x plus iy, the x value and with respect to y value. Whatever we draw in the graph, by using that we can find out the mod value. That is square root of x square plus y square. That is absolute value. And conjugate is, suppose if I take z is x plus iy, its conjugate is x minus iy. So for this I will tell one beautiful story how we can relate real numbers to complex. Whenever you are studying complex, you should compare with you should match with the real plane and complex plane. I will tell you one beautiful story. Actually, one person is there. His name Fermat. I think all of you are aware about Fermat's last theorem. That person is very peculiar person, very interesting person, Fermat. Usually, whenever you will get any invitation for webinar or conference, you will never accept. You will never accept that invitation. Then what he will do? He's a great mathematician, Fermat. So the thing is, he is very special person. Whenever suppose any international conference are going on his days, on any international conference, and he will only go himself. Though they are not inviting, sometimes if he got interest, he will only go to that respective conference or webinar places, and he will write directly. He will enter into the dais. Directly, he will enter into the auditorium, and he will write his problems, his mathematical problems, unsolved problems. In this way, he is very special. Sometimes they may invited him for any talk, any webinars, he will not accept. But sometimes he will, without invitation, he will only go. So one time he went to one place. That is a place with all mathematicians. That is a place containing all mathematicians from the world. So all mathematicians gathered in that place. So directly he will enter into that conference place, and he will write one problem. He will write one problem on the board. What is that problem? That is x power n plus y power n is equal to z power n. That is the Fermat's last theorem. X power n plus y power n is equal to z power n, and where x, y, z are positive numbers. X, y, z are positive numbers, where n value is greater than 2. N value is greater than 2. He asked the solution. He never explained any solution. He not given any clue about the solution. Proof. Simply he posed that problem in the conference. X power n plus y power n is equal to z power n, where x, y, z are positive integers. Remember that x, y, z are positive integers, and the n value is greater than 2. What about n less than 2? If I take x square plus y square is equal to z square, is there a solution? Yes. Triplets, Pythagorean triplets. We can take 3 square plus 4 square. What 3 square plus 4 square? 25 is equal to 5 square. 25. So 25, left hand side 25, right hand side 25. Less than 2 possible. So x power n plus y power n is equal to z power n. N less than 2 possible. You can find out the solution. X square plus y square is equal to z square. We can find out the Pythagorean triplets. Then what about the case of n greater than 3? So n greater than 2. Suppose if I take x square, x cube plus y cube is equal to z cube. What is the solution? X cube plus y cube is equal to z cube. What is the solution? So he posed this problem on the conference. It is a place with all mathematicians from the world. Nobody solved that one. Nobody knows the solution. That is the problem posed by Fermat on that conference. So that is unsolved. That problem is unsolved for so many years. I think after 40 years, a great mathematician, Cornwallis, he proved that he gave a proof for this problem. Is x power n plus y power n is equal to z power n, where x, y, z are positive integers and n is greater than 2. Cornwallis gave a solution with 355 pages. He wrote a thesis on that problem. See, Fermat's one theorem leads to one thesis. What is a great thing? What a great mathematician Fermat. And after Cornwallis, I think you know about Cornwallis. He is the teacher of, or is the guide of Indian field medalist Manjula Bhargava. Many people don't know. He is the Fermat's last theorem. For Fermat's last theorem, the one great mathematician gave proof. That is Cornwallis. Cornwallis' student is Manjula Bhargava. He is a famous Indian field medalist. I think 3 years back he got field medalist for his mathematical work. Manjula and Andrew Wallace is the Manjula Bhargava. He is the student of Andrew Wallace. So Andrew Wallace gave Andrew Wallace gave a solution for the Fermat's last theorem. And what the relation between Manjula, we should know, because he is a field medalist, a great mathematician Manjula Bhargava. Manjula Bhargava is the student of Andrew Wallace. This is about solution. How we can expect from what about the problems on mathematics? The unsolved problems on mathematics. Unsolved problems on mathematics. Like it is similar to Navier-Stokes equation. I think recently some mathematician we heard that mathematician proved that one. No, then completely they not proved that Navier-Stokes equation. For some special cases they proved. Still they got solution for some special cases. But it is a millennial question. Navier-Stokes equation is a millennial question. Still it is unsolved. So these are the unsolved problems in mathematics. So what is the Fermat last theorem? The Fermat last theorem, that is with respect to the real number system, means real plane. Then come to so if, like that complex plane also, for finding, why I said all this story is like that complex analysis also, for finding the square root of a negative number, this theory build up, this theory introduced. So how we can like similar to how you add the two numbers in real plane. So here also addition takes place like this: a plus bi into c plus di means we have to add the respect to real part and respect to imaginary part. You can see b plus t is the imaginary part, and multiplication also. These are all known things, and you have to take the conjugates. Here 1 divided by a plus b by bi, we have to multiply and divide by a minus bi. So you will get a minus bi by a square plus b square. You can see here, and 1 by z is equal to, so a, if you take z as complex number x plus iy, then it will become z bar divided by rationalizing the denominator. Here in division we have to go for rationalizing the denominator. That we can write in the form of z bar and in the denominator we can see in numerator 1, in the denominator z. After rationalizing the denominator, you will get z is equal to x plus iy, so that it will become x minus iy. Z bar means x minus iy divided by mod z. Mod z means square root of y square, means x plus iy into, sorry, mod z is equal to x square plus y square. Then how it comes means z is x plus iy. Again you are multiplying with x minus iy. X plus iy into x minus iy, you will get x square plus y square. X square plus y square. This is about how you write the 1 by z bar divided by mod z. Next, come to the my presentation, today's topic, that is analytic functions. Analytic functions, here you have to concentrate. In two ways we are going to define analytic function. In two ways. One is first point, a function is said to be an analytic function at the point z0 if it is differentiable at that point and also its neighborhood. Usually you will come across this definition only. An analytic function, a function f of z is defined on a complex, defined on omega, any domain. We are taking a domain sigma. A function which is defined on a omega is defined on a domain omega. Omega, what is domain? Open and connected set. When we say domain means it represents open and connected. Open and connected reason we are going to call it as a domain. So when you are defining a function f of z over a domain sigma, when we say it is analytic, at a point z0 in omega, a point the point z0 is in the region omega. When we say it is analytic means, one first definition, it is differentiable at that point and also its neighborhood, its surrounding points, and also its neighborhood. That is the definition of the analytic function. So then what I am saying is different, what is in the slide is different. So in another way also you can define. With respect to differentiability, I define like that. If any function is differentiable at that point and also its neighborhood, we are going to say it as a analytic function. Actually, for that you may study different theories are there, different properties are there based on Cauchy-Riemann equation, CR equation. Means if I take f of z as u plus iy, if I define a complex function f of z as u plus iy, dou u by dou x is equal to dou u by dou y. Means ux is equal to uy is equal to minus vx. That you know, CR Cauchy-Riemann equation. That is a necessary condition. A function, if it satisfies a CR equation, you are going to say it is an analytic function. Whether this is sufficient? No. In a function, not only a CR equation, not only the single condition for to say the function is analytic. If the function is analytic, obviously you can say that it satisfies CR equation. Come to vice versa. If the function is satisfies CR equation, can we say it is analytic? No. We cannot say it is analytic. Because one more condition is that is the whatever I said, the partial derivatives dou by dou x, dou by dou y, dou by dou x, dou by dou y is ux, uy, vx, vy. All these partial derivatives must be continuous. Means if the function satisfies CR equation, and also the partial derivatives are continuous, then we can say the function is analytic. I am clear. If the function is analytic, damn sure it satisfies CR equation, Cauchy-Riemann equations. If you come to the converse, if the function satisfies CR equation, can we say it is analytic? No. It has to satisfy CR equation, and also the partial derivative should be continuous. Then we say the function is analytic. This is about necessary and sufficient condition for the function is said to be analytic. That is another part. Now what I am giving is a function is said to be analytic in the domain sigma at the point z0 is giving the explanation. It can be represented in a power series expansion. This is another definition. It can be represented in a power series expansion. You can see here summation Cn into z minus z0 whole power n. In n is a n must be greater than or equal to 0. We see this condition. N start from the 0. N start from the value 0. Suppose here in place only positive integers here is considering. What happens if we take negative values? Negative values, it will reduce us to the Laurent series. That is after that it leads to the Meromorphic function. That is a different case. Later we can discuss that. First we can go for analytic function. This is second definition. A function. This is with respect to the complex plane. Whenever the function is said to be analytic at the point z0 in omega, it can be represented in that function can be represented in the power series expansion with respect to the point z0. This is about complex plane. So up to this, you just think it once. What were defining this analyticity of analytic function? You can correct another different names. Analytic function, regular function, okay, holomorphic function. This analytic function you can correct away synonyms: analytic function, holomorphic function, and regular functions. So this is whatever you are defining analytic function, that is on the complex plane. What about real plane? Just think it once. Can we define these analytic functions on a real plane? Yes, but how we define? What is the definition? How we are going to define it in real plane? Usually, whatever you are getting seeing the definition, that is on complex plane only. What happens if it comes to the real plane? Can we define analytic function? Yes, we can define analytic functions on a real plane. How means if the same function is possible to express in terms of Taylor series, then we say the function is analytic function with respect to the real plane. This is with respect to the complex plane. That function should be represented in the power series expansion. If it comes to the real plane, it should satisfy the Taylor series expansion. Okay, that you should clear. Then you can see the example here: 1 divided by 1 minus z. How we expand then see the expansion 1 plus z plus. This expansion, you can observe the thing is analytic for mod z less than 1. Why mod z less than? It should be less than 1. You should think why mod z is less than 1. This you should understand. It is an analytic function with respect to the reason mod z less than 1. Why mod z less than 1 is, you can see it is a geometric series. It is convergent with respect to the reason mod z less than 1. A geometric series, it is convergent with respect to the reason with respect to the point mod z less than 1. That's why this condition is important. Mod z less than 1. In this reason only, the function 1 divided by 1 minus z is analytic. So because you are seeing in the power series expansion, but with respect to the condition mod z less than 1. Why mod z less than 1? Because it is a geometric. It represents that function represents geometric series. With respect to mod z less than 1, it is convergent. Next, come to the e power z. You can see the expansion here. How we expand this is well-known expansion. This common expansion z plus 1 plus z by 1 factor. See this expansion, and it is analytic over the plane. Mod z less than infinity. Mod z not any value 1, 2, 3. No, it is taking to infinity. Mod z less than infinity means over the plane. So this leads to the analytic function over the complex plan means that will lead to the entire function concept that we can study later. A function, an analytic function, analytic in the whole, a function which is analytic in the whole complex plan is said to be entire function. Then all analytic functions are entire functions. All function, all analytic function, no, because with the analytic function, that concept you are going to define with respect to the domain, in the complex plane. But the entire function concept you are going to define in the whole complex plane. Is it clear? Analyticity or analytic function concept you are going to explain in the domain of the only with respect to some domain, with respect to one individual domain in the complex plane. That is analytic function. What is the then what is the entire function? Whether all analytic functions are entire functions? No, because in some functions they may be analytic in the domain. Some maybe it fails in the whole complex plane. It may fail in the whole complex plane. That's why all analytic functions will not say entire function. Okay, this is a difference. You should be clear that for analytic function you are going to define with respect to the domain, and entire function you are going to define with respect to the whole complex plane. These are with respect to these two examples you can understand. And this is whatever I said, the meromorphic or complex differentiable. This is the definition of the another definition. I said a function is said to be a function is said to be analytic at a point z naught, if they exist, if it is differentiable at that point and also its neighborhood. This what it represents, f dash of z naught is equal to limit delta tends to 0. This is the definition of differentiability. Before only I said this definition of analytic function with respect to the differentiability. That only is going to tell in the explaining this in this slide. Take this another three functions. E power z is analytic functions. That how is the expansion of this is a power series expansion of e power z. E power z is an entire function. E power z is an entire function, and you can see the sin z. Sin z is equal to this is the expansion of sin z. How you expand the sin z, and this is a power series expansion of cos z, and the power series expansion of 1 z by 1 minus z. So all these are the example for analytic functions. Analytic function. I already said a function is said to be analytic in the at the point z naught in the domain omega. When it is possible, when we say it is analytic function, it is possible to write the given function in the terms of power series expansion. So we can see e power z, you can write the power series expansion. Sin z is the power series expansion. Cos z 1 z by 1 minus z. Okay, all these are example for the analytic functions. Suppose if anybody asks what is the example for, and you can give this e z, sin z, cos z 1 divided by 1 minus z. These are the example for the analytic functions. This is Euler's formula. How we use in place of theta, in place of e power z, he consider I theta, and after that he is in this. This is simple explanation. This is with respect to the polar coordinates. Instead of x comma y, if you take r theta with respect to the polar coordinates, so e is defined. E power I theta is equal to cos theta, cis theta. E power I theta is equal to cos theta plus I sin theta. This is also with respect to the polar coordinates. Because mainly I went to the rational functions. Rational functions, that means the functions which can be expressed in the form of ratio of two polynomials. You can look here. Ratio of 2 pi, he is giving the one rational function z divided by 1 minus 5z plus 6z square. Z divided by 1 minus 5z plus 6z square. This is a rational function because it is a fraction of two polynomials. You can see numerator contains polynomial of degree 1. You can see the denominator contains a polynomial of degree 2. How to simplify it? By using partial fractions. You just to simplify, if you convert the quadratic equation to linear factors. 1 minus 5z plus 6z square. How to convert that quadratic equation into linear factor means it will convert to 1 minus 3z into 1 minus 2z, and after that by using partial fractions you can solve. That means it is the solution of the rational functions. This is the solution. Finally, by using partial fraction you can easily, if you have idea about partial, a little bit idea about the partial fraction, you can solve this. You can find out you can simplify these rational functions. Rational functions ratio of two polynomials. Numerator also contains polynomial, denominator also contains polynomials. This is also one. We can look at this is a cubic equation. This is a rational function. This is because it is a ratio of two polynomials. Numerator is a polynomial of degree 1, denominator is a polynomial of degree 3. How to convert the first we have to look at the denominator part, that is a cubic polynomial. Cubic polynomial we have to convert into linear factors. How it is 1 minus 2z into 1 plus z square. The 1 minus 2 1 plus z square is a quadratic equation. 1 plus z square is a quadratic equation. So by again, if you have a little bit idea about the partial fraction, we can by using C0, C1, by taking the constant values, we can simplify these rational functions. This is a simplification of rational functions. So this is whatever I explained up till now, that is with respect to the theoretical part. Because nowadays, without practical application, without the laboratory work, without the softwares, without the technology, that is very, very difficult to survive, very difficult to survive in that theories. That's why now by using Mathematica, how to draw this series, how to draw the power series, okay, how to execute the power series, that we can see here by using Mathematica. This is Wolfram means by using Mathematica. Just if you enter the function, you see here you can see how to write the function means. You can observe series z divided by 1 minus 3 star represent multiplication plus 4 star z cap 3 means this is the just if you enter the this rational function with like this one with this z divided by and within the bracket 1 minus 3 star z plus 4 star z cap 3 means 1 minus 3 z plus 4 z cube. If you enter here, if you give this code, if you this code, then that will execute this series. You can see summation n is equal to 0 to infinity directly. No need to solve now. No need to solve. Okay, that is only if you just enter the series, that will generate just enter the function. Just if you just enter the rational function, that will generate the series. What is the coding? Series z divided by within the bracket 1 minus 3 star z plus 4 star z cap 3. If you enter this program, this coding, say series of this function, then immediately that will generate the series. This is by using Mathematica. If you enter the problem, that will generate the power series. So why it is required? Because if you by using that power, by using that power series, we can say whether that function is analytic or not. It should generate some power series. How so manually it is not, it is difficult. If you have to go on solving manually for all the problems, sometimes it is typical, it is tedious. That's why at that time you have to make use of this Mathematica. By using this, we can generate the series for the given. We can generate the power series for the given rational function or given function. That you can observe here and see that will give the reason also. See z divided by 1 minus 3z plus 4z cube with respect to the region mod z less than 1 by 2. With respect to the reason mod z, that will only give the reason with respect to the reason mod z less than 1 by 2. Come to the second one, 1 plus z square plus z cube divided by 1 minus z square minus z cube minus z square 4. What about this function? So here after executing here, you are seeing series expression at z is equal to 0. It is telling that whatever the series generated, it will only predict whatever the series generated from that programming. That series is a series expansion at z is equal to 0. So by using mathematical tool also by using this Mathematica, we can generate this series. Next come to the this is a more analytic function definition. Come here. Meromorphic functions. This is after I said analytic. I explained what is analytic function, what are the examples, and what are the. Is there any apps? Is there any mathematical tools to derive that series for the function? Everything over. Now meromorphic functions. Analytic function and after the entire function means a function which is analytic in the whole complex plane, we are going to say it is a entire function. Then meromorphic functions. So here, if a function is said to be meromorphic, a complex function is said to be meromorphic, if there exists a pole. Simple definition you can say it. If you find out a poles, you can say it is meromorphic. Otherwise, analytic in the whole complex plane, except at some poles. See the gap between entire function and meromorphic functions. Gap between entire function and meromorphic function. Yeah, so if it is analytic in the whole complex plane, entire function. It is analytic in the whole complex plane except at some poles. It means if you find out any poles, then we say it is a meromorphic function. Meromorphic. That only is explaining here. Meromorphic with respect to, and he is giving different definition. What I said, poles means what is that poles? 1 by z. Suppose if you take z is equal to 0, take simple function f of z as 1 by z. F of z as 1 by. If z is equal to 0, then that function tends to infinity. That function tends to infinity. So then that z is equal to 0, I am going to call it as a pole. Pole of order 1, because 1 by z. What is the power of z? Z power, it is 1 only. Z means z power is 1 only. So it is a simple pole. It is a simple pole. Then what are the multiple poles? So if I take if you replace 1 by z by 1 by z square, what is the power of z? 2. So you can say, then if you take z is equal to 0, again 1 by z is equal to 0 means 1 by 0 square. 1 by 0 square means again you will get infinity only. So at z is equal to 0, you are getting infinity. So z is equal to 0 is a pole of order 2. It is a multiple pole. Like that, you can take any orders. Single order, double order, of order 3, of order 4, depend on the denominator function. Depend on the denominator function. That is only is defined here. A function represents the form of rational function. F of z divided by g of z, here f of z, g of z are analytic at z naught. This is the here this meromorphic definition also defined in 2 ways. A function which is analytic, a complex function which is analytic in the whole complex plane, except at some poles, we are going to call it as a meromorphic functions. So you can see some examples so that it will become very clear. And I already explained what is pole, simple pole, multiple pole. You can see in the slide also. Is defining h minus m divided by z minus z naught whole power m up to that z square, z minus z naught whole square. See the denominator function just, and z minus z naught. All these. So here you can observe negative powers. Negative powers. Where you can see the power series expansion of analytic function, you will see the positive powers. Here you can see the negative powers. See z minus z naught whole power m, capital M. Next, how we defined the h of z. H of z. H suffix minus m divided by z minus z naught whole power m, and plus h minus 2 z minus z naught whole square, h minus 1 divided by z minus z naught. So here you can see the negative powers. This is called Lorentz series. Negative powers of z minus z naught means this is representing the Lorentz series. For this is going to define it as a pole of order m. See the power of in the first function h of z, z minus z naught whole power capital M. What is its power? Power is m. Pole of order m. That is called the order. That capital M is going to call it as a, that is the highest value. That highest value are going to call it as a order m at the point z naught only. At the point z naught. So before from analytic function to meromorphic function, before one in between, I said already what I said. A function is said to be a meromorphic function. A complex function is said to be meromorphic function if it is analytic at the whole complex plane, except at some poles. Then some poles means you can see that analyticity fails. At that point means at the point of pole, the function fails to be analytic. For that, we are going to define it as a singular points between analytic function to meromorphic function. There will be that gap is filled by singular points. Singular points you also divided into removable singularity, essential singularity, non-essential singularity, isolated singularity. So whatever it may be, if any whatever the type of singularity, either it may be removable singularity, essential singularity, non-essential singularity, removable singularity, that will not represent the entire function. That is totally different. Entire functions and entire function means the function which is analytic in the whole complex plane. So there is a difference between entire function and with respect to all these singularities, that may be a removable singularities, both are totally different. Because removable singularity means that is also one type of singularity, and isolated singularity, that is also one type of singularity. So there is no matter of entire function. There is no matter of analytic in the word complex manner. That's why there is a difference between these two. Removable singularity, isolated singularity means you cannot find any other singularity within nearer to that point, or in the neighborhood of that point, in the domain of that point. You cannot find other singularity. That's why also isolated means that is the only one singularity. That is the only one singularity. You will not get any other singularities. Okay, that is isolated singularity. If you get a singularity, more than one singularity in the domain, in the same with that point, in the domain of that point, in the neighborhood of that point. Once again, I am repeating. If you get more than one, if you get more than one singularities at that point, and also its neighborhood, near is surrounding to its that point, you will get another neighborhood also, you will get another singular point also there exists. So for every for another neighborhood, another singular point will exist. So this is going to call it as a non-isolated singularities. Singularities. You can see the circle of singular points. Within that domain, you can see so many singular points. That type of singularities we are going to correct as a non-isolated singularities. Suppose if it is possible to remove the singularity, then we are going to say it as a removable singularity. We are going to say it as a removable singularity. Suppose if you take, if you define the function f of z as sin z, where z is not equal to 0, if we just simply define the function as sin z by z, sin z by z. Suppose sin z by z, if it is z not equal to 0, if how the function is defined means f of z is sin z by z where z not equal to 0, and take f of z as 1 if z equal to 0. F of z is equal to 1 if z is equal to 0. So this is, you can remove this singularity. You can just remove this singularity So this is, so up to this I explained this entire function and Meromorphic function. So here we come across, these are the results. Usually we whatever up to this I explained Meromorphic functions. So by using that Meromorphic function, we are going to prove the uniqueness property. Uniqueness means, suppose if I take two functions f and g, when it is unique, when it is going to be unique, with respect to what boundary condition, what are the conditions required to show it is the two functions unique. For this, I'm making use of Naveenkumar characteristic function. This is also called value distribution theory. With respect to the sharing value, with respect to the zeros, poles, we are going to say we are going to prove the uniqueness property. T represents the Naveenkumar characteristic function, and M represents the proximity function. N represents the counting function. So these are the notations. So without poles, with poles means this bar represents, we only if n is there means we have to consider both zeros and poles. Consider zeros and poles. This bar represents means you have to ignore the multiplicities. We have to ignore the multiplicities. Nk bar of 1 comma divided by f minus a, where a is the sharing value. Sharing f. See, you can see the definition. Nk bar of r comma, and see that bracket. K after the bracket and a bracket with respect to k. What it represents? The counting function for the zeros of f minus a with multiplicity that represents the multiplicities. Multiplicities greater than or equal to k and multiplicity less than or equal to k. That you can observe here, the notations. These are all the notations used for counting the zeros and poles. Nk. Sharing value Ek, with respect to the weight also. Ek means that is with respect to the weight a comma f. A function f share the value a with respect to the weight k. With respect to the weight k. That only is represented by e of a comma f. E of a comma f. You can see the definition here. F of z and g of z be two non-constant meromorphic functions. I have already informed you. I already explained you. Now I am going to show the uniqueness between two meromorphic functions. So what are the two meromorphic functions here? F of z and g of z. So here f minus a and g minus a are the poles of f of, are the, with respect to the zeros and poles, and with respect to the ignoring multiplicities. We say that f of z and g of z share the value a counting multiplicities if they coincide in locations only. And we say that f of z and g of z share im represents the ignoring multiplicities. Ignoring multiplicity means, suppose I can give an example. 1 by z square. 1 by z square means, what is its multiplicity? 2. Its multiplicity is 2. So here whenever I use the word ignoring multiplicities means I cannot count that power 2. Means you have to take it as simple pole only. You have to consider it as simple pole only based on the result. Counting multiplicity means we have to take both its poles, and you have to consider its multiplicity also. That we explained that I am showing in this slide. This is about these are the previous the previous results. So here, with respect to the functions f and f power k, kth derivative with sharing 1 cm, with respect to sharing 1 cm is one counting multiplicity, and with respect to this condition 2 n bar of r comma f, n bar of r comma 1 by f dash, with respect to this condition, and where the lambda lies between 0 and 1, lambda lies between, because less than or equal lambda plus order of 1 represents the error term. With respect to this lambda value, he proved that f power k minus 1 divided by f minus 1 is identically equivalent to c. Either identically equivalent to c, or you can say it as f power k derivative is identically equivalent to f. These are the previous results. And this is also f power k with respect to, here you can see one counting multiplicity, here you can see a counting multiplicity. With respect to f and f power k, with respect to the a counting multiplicity, and with respect to this condition, finally they proved that, see, when f power k share a counting multiplicity, and with respect to this condition, means 4 delta 0 comma f plus 2 8 plus k theta of g infinity comma f greater than 19 plus k, then f is equivalent to, f is unique to f power k derivative. F is unique to F power K. Whatever the property satisfies for the F, that will satisfy for F power K derivative also. That is the main thing. Here is considered meromorphic functions. So this is our result. Here, in the previous results, you can observe the functions F power and F power K derivative only. F power and F power K derivative only. But here we consider, instead of F power K, you generalize that results. Generalize that results means in this F place, you consider Fn P of F means generalized polynomial and Fn P of 4 power K. So totally we generalize all the our theorem generalize all the previous results. So this is a improvement. This is the improvement what we have done compared to the previous results. Instead of the functions, we consider the polynomial. Polynomial means we can substitute any function for that polynomial. The P of F means you can take a function of F power K derivative. What are the derivatives you can take in the place of P of F? That only we did here. Fn P of F, the Fn P of F 4 power K. These are our results. So here also, with respect to so for this function, this is the condition. Lambda that must be lies between 0 and 1 only. Lambda should be lies between 0 and 1 only. With respect to this condition, with respect to this condition, and here you can observe. He is using E. E means E with respect to the weight L only. With respect to the weight L. L represents the weight, and see the function here. The sharing value is E. Sharing value is small a. That's why EL bar of A comma Fn P of F, A comma Fn P of F is what small a represents. Small a represents the sharing value. Small a represents the sharing value. So that Fn P of F, Fn P of F whole power K. With respect to this condition, we are going again. Our result proves that Fn P of F whole power K is identical equivalent to Fn P of F. We can write this one as Fn P of F whole power K is identical equivalent to Fn P of F. This is our result. Our results generalize all the previous results. So then also here we are considering Fn P of F, Fn P of F, Fn P of F, its derivative. And nowadays, the recent research is going on. The trend is going on L functions. Why we are going switching from meromorphic function to L functions means L functions we are analytically considered as a meromorphic functions. L functions analytically can be considered as a meromorphic function. Means whatever the property satisfies for the meromorphic function, that are going to satisfy for L functions also. Maximum that the properties of the meromorphic functions approaching to the properties of the L function. That's why they are replacing this meromorphic function F by L. See, it's very simple thing here. They consider the sharing value as small a. A may be a function, small function. The two functions Fn P of F, Fn P of F 4 power K. They can share a value 1 cm. They can share a value 1 im. They can share a value small. So this is a small function. And also nowadays the work is going on. Instead of taking the two meromorphic function, they are taking one meromorphic function as F. And they are taking one meromorphic one in the place of meromorphic function L. Instead of Fn P of F or Fn P of F 4 power K, or similarly simply F and G. Instead of F and G, they are considering F and L. F is a meromorphic function. L is represent the L function. Why L function? Because L is also analytically considered as a meromorphic functions. This is the research work going on present. They are taking instead of F and G, where F and G are meromorphic functions. Likewise, they are taking L1 and L2. L1 and L2. L1 is a L function. It means both are taking L functions. Both are taking L functions means both are we have to consider as a meromorphic function only. Both L1 and L2 we have to consider as a meromorphic function only. Those are approaching to meromorphic function because whatever the property satisfies for the meromorphic, they are going to satisfy for L function. So there is work is what they will do simply they will take two meromorphic functions. Instead of taking two meromorphic functions, they will take two L functions L1 and L2 with respect whatever may be the sharing value. That may share the value 1, that may share the value small function A, small a, that may share the value A ignoring multiplicity. They go on changing they keep on changing the sharing values. They go on keep on changing the sharing values for the two L functions L1 and L2 and with respect to what condition? With respect to what condition? That two functions are equivalent. Here you can see here f and pff is equal to f and pf whole power k. Like that, with respect to some condition, what is the condition here? 3k plus 6 theta infinity f. This infinity represents the pole. 3k plus 9 theta of 0 comma f 0 m delta 0 comma f 0 represents the zeros. So with respect to this condition, the two functions f and pff and f and pf whole power k is equal. Like that, with respect to some condition, with respect to some sharing values, L functions, two L functions L1 and L2 become equal. This is about what is the current research work. Instead of taking Meromorphic function, instead of taking directly Meromorphic function, they are taking L functions. So for proving our result, we require some lemmas. These are the helping part for the proof. This will help for the proof of our results. These lemmas will help for the proof of our results. The references we have gone to the for our results. It's all about today's presentations. Is there any doubts?
Sir, just we ask the students for the questions, sir.
Yes.
We're
Any
waiting.
doubts?
If any questions? Till now, there's no questions, sir.
Yes, sir. Any doubts?
Sir, there is no questions, sir.
There are
There's
no
no
questions.
doubts. Yes, sir.
Okay, thanks.
Okay, thank you.
Okay.
Sir, we'll go for
Thank
a
you,
formal
sir.
vote of thanks, sir. Formal
sir.
vote of thanks. Yeah.
Hmm.
So this is given me great pleasure to thank us one and all. First, I express my gratitude to our college secretary, Shri Ashok Kumar Mundraji, then our college principal, Dr. S. Santosh Babu, and convener and head, Department of Mathematics, DG Vaishnava College, to given the permission and make this webinar happen. And the main thanks to today's resource person and the today's guest of honor, Dr. Naveenkumar from Presidency University, Bengaluru, has given us a wonderful thought and shared his valuable time with us to introducing and clearing and verified all the apt examples and explained and inspired to study that subjects more on his spot side. Then who are attending this webinar, so for one and all, it's a thanks again. Now,
Thank
as
you.
we put
Thank
your
you.
feedback link and our chat box, kindly is fill it up.
Thank
And thank you
you,
very
sir.
much, sir.
Thank you from my side. Thank you. I'm thankful to Dwarakadas Govardhan Das Krishna College for giving this wonderful opportunity, sir. Thank you. Thank you very much.
Sure, sure, sir. Thank you, sir. Thank you very much,
Thank you.
sir.